In this tutorial, we'll be discussing the background and the foundation for the quantum mechanical model. Alright, so in the previous tutorial we talked about the Bohr model. The great success of the Bohr model of an atom was that it predicted the lines of the hydrogen emission spectrum. However, it failed to predict the emission spectra of other elements that contain more than one electron. For this and other reasons, the Bohr model was replaced with a more sophisticated model called the quantum mechanical or wave mechanical model. The quantum mechanical model of the atom replaced Bohr model in the early 20th century, and the quantum mechanical model, Bohr orbits, were replaced by quantum mechanical orbitals. Orbitals are different from orbits in that they represent the probability that show a statistical distribution of where the electron is likely to be found. Quantum mechanics revolutionized physics and chemistry because the quantum mechanical model, electrons do not behave like particles flying through space. We cannot, in general, describe their exact paths. An orbital is a probability map that shows where the electron is likely to be found when the atom is probed. And it does not represent the exact path that the electron takes as it travels through space. So this is referring to the likelihood of finding an electron. Alright, so let's take an analogy of baseball. Imagine that the baseball throws a pitch and the catcher at the home plate. The baseball's path can be easily traced if it travels from the pitcher to the catcher, and so therefore the catcher can catch it. In the quantum mechanical world of an electron, the catcher could not know exactly where the electron would cross the plate for any given throw. So it's like having a catcher that's blind. You can know the probability of where that ball is going to land, but you don't know it exactly. He would have no way of putting his mitt in the right place to catch it. However, if the catcher kept track of hundreds of electron throws or baseball throws, he could observe a reproducible statistical pattern of where the electron crosses the plate. He could even draw maps in the strike zone showing the probability of an electron crossing a certain area. These maps are called probability maps. So here we go here. So 20% of the time it lands right smack dab in the middle. 40% of the time it lands within this circle. 70% of the time it lands within this circle. So anywhere from here on in is 70% of the time. From here on in is 40% of the time. The exact bullseye would be about 20. To describe the behavior of a pitched electron, you would have to construct a probability map of where it would cross the home plate. In a quantum mechanical model, a number and a letter specifies the orbital or orbitals. The lower energy orbital is the quantum mechanical model is called the 1s orbital. It is specified by the number 1 and the letter S. Alright, so let's talk about the 1. The 1 is the principal quantum number. It specifies the principal shell of the orbital. So when we look at this map, and we have the nucleus, and then the rings on the outside. The first ring is 1, the second ring is 2, the third ring is 3, so on and so forth. That's the principal quantum number, is what number ring it is out. That's the principal shell. The single electron of an undisturbed hydrogen atom at room temperature is in the 1s orbital. This is also called the ground state or lowest energy state of the hydrogen atom, meaning it's the most relaxed. The absorption of energy by the hydrogen atom can cause the electron to jump from the 1s orbital to the higher energy orbital. When the electron is the higher energy orbital, the hydrogen atom is said to be excited, in the excited state. So in previous tutorials, once again, here's the nucleus, here's the rings around it. So this is the first energy level, the first ring. That's where the electron is normally. Normal would be ground state. Then electricity or something excites the electrons and it jumps to, let's say, the third energy. This is now considered the excited state when it goes up. All the atoms of each element have one ground state and many excited states. So in other words, even though the 1s is the most normal, the ground state for the hydrogen, it could jump to a couple of different variables and have multiple different excited states. The higher the principal quantum number, the higher the energy of the orbital. The possible principal quantum numbers are whole numbers, 1, 2, 3, 4, so on and so forth, with energy increasing as n increases. So here's the center, the energy goes out, the rings go out, and as that happens, n goes out. Since 1s orbital has the lowest possible principal quantum number, it is the lowest energy shell and has the lowest possible energy. The letter indicates the subshell of the orbital and specifies the shape. So the possible letters are S, P, D, and F, each with a different shape. Orbitals within the S subshell have a spherical shape. Notice this is 1s and this is 2s. 2s is larger because it's further out. So as these go further away, the orbitals get bigger. The possible letters, once again, are S, P, D, and F, each with a different shape. So S was here. Here's P. It looks kind of like a dumbbell. And here's D. D and F are far more complicated. This is like two dumbbells that are crossing, like a four-leaf clover almost. The F shape is like this, except there's two four-leaf clovers on top of each other, and it gets really complicated looking. It's really hard to draw, so I apologize for that. Orbitals are sometimes represented by dots where the dot density is proportional to the probability, not 100% probable, of finding an electron. The dot density for the 1s orbital is greatest near the nucleus and decreases farther away from the nucleus. So here's the atomic nucleus. Here's the probability density. The dot density for the 1s orbital is greatest near the nucleus and decreases farther away from the nucleus. That's what I just said. The electron is more likely to be found close to the nucleus than far away from it. Orbitals can be represented by geometric shapes that encompass most of the volume where the electron is likely to be found. Those were the four shapes we just saw, S, P, D, and F. The 1s orbital can be represented as a sphere that encompasses the volume within which the electron can be found approximately 90% of the time. If we superimpose the dot representation of the 1s orbital on the shape representation, we can see that most of the dots are within the sphere, meaning that the electron is most likely to be found within the sphere when it's the 1s orbital. So here we have the dot density, and here's the shape. If we superimpose those two, notice that most of the dots are within that sphere. The dot density and shape representations of the 1s orbital is here. The dot density is proportional to the probability of finding the electron. The greater dot density near the middle represents the higher probability of finding the electron near the nucleus. The number of subshells is a given principal shell is equal to the value of n. So in other words, we have 1 here, so we have 1 subshell. We have 2, so we have S and P. We have 3, S, P, and D. We have 4 S, P, D, and F. The 2s orbital is similar to the 1s orbital, but notice that it's bigger, it's further away from the nucleus. The 2p orbitals, this figure shows both the dot representation on the left and the representative shape on the right for each p orbital. Notice that there's 3 p orbitals. This becomes important later on, whereas here there's only 1 s orbital. Orbitals when n equals 3. The next principal shell is n is equal to 3, which contains, hence, 3 subshells, S, P, and D. So the S is still going to be the sphere, the P is still going to be those dumbbells. Now we're adding those clovers. The S and P subshells contain the 3s and 3p orbitals, similar to the shape in 2s and 2p, but slightly larger and higher in energy. The D subshell contains 5 d orbitals. So there's 1 s orbital, there's 3 p orbitals, now there's 5 d orbitals. 1, 3, 5. Those numbers become important later on. The figure shown here is the dot representation and the shape representation for each of the d orbitals. There's 5 of them. Here's the first 4 just look like clovers. The 5th one's a little bit different. The quantum mechanical model predicts the bright line spectrum of hydrogen as well as the Bohr model does. The quantum mechanical model can predict the bright line spectra of other elements too. The Bohr model cannot predict spectra for atoms with more than 1 electron. The Bohr model was replaced with a more sophisticated model called the quantum mechanical or wave mechanical model, which is what we've been representing in this last tutorial. The Bohr model is still important because it provides a logical foundation for the quantum mechanical model, so we don't want to throw it out, but we wanted to add to it, and reveals the historical development of the scientific understanding.